Today, what we will be reviewing is some case examples of some catastrophic failures, trying to pinpoint why those failures happened. Cables, testing. Maybe we should have done a little better testing. Talk a little bit about built-in tests functionality, and then move over to verification and validation to ensure that some of these catastrophic failures do not happen. And then talk a little about hardware in the loop, system integration labs, hybrid test benches, moving on to Vistas, and then of course, questions and answers. So let's start. So system failures in any industry, from aerospace and defense to oil and gas, have had catastrophic results with lives and assets lost. And yet many such events could have been avoided with advanced design, verification, and testing tools and techniques. System verification coupled with built-in tests and diagnostics are crucial to sensing and diagnosing these failures, potentially saving lives, billions of dollars in liabilities, and of course, our reputation. So does anybody remember the Deepwater Horizon catastrophe? It was actually way back in 2010 in the Gulf of Mexico. Well, this one, there were unfortunately 11 people died, 17 people are injured, greater than $61 billion of liability losses. It's the worst disaster I can think of, maybe except for some of the nuclear ones at Chernobyl and Fukushima. So what was the cause? What was the cause? How could this have been avoided? The U.S. Chemical Safety and Hazard Investigation Board actually studied this and released their study back in 2016, outlining the various failure modes that led to this disaster. And it's still relevant today. So I don't know if anybody recognizes this, but this is a blowout preventer. Like most disasters, there was a stack up of many different failures. There's one device that is the last man standing in these oil rigs. If all else fails, which in this case they did, this is supposed to work. It's called a blowout preventer, and it's there to contain the uncontrolled release of oil. It has two redundant, a total of 4 solenoids to actuate the hydraulic and mechanical shutoff valves. They both have 2 battery backups in case of the loss of power from the top sides. This is a basic block diagram of the solenoid control system for that blowout preventer. It has 2 redundant, a total of 4 solenoid controllers to actuate 2 solenoids controlling the hydraulic and mechanical shutoff. They both have 2 battery backups in case of the loss of power from the top sides. On one side, the yellow side, both solenoid controllers were miswired and shorted to the battery, so they were dead. The other side, only one was miswired, and of course that led to yet another dead battery. The operator on top sides had no diagnostics or checks to ensure that they were wired properly, to ensure that the batteries were functional, or even to ensure that the solenoids would actually work. They gave the command to actuate, stop the oil, blindly, without the ability to even check if anything else was alive down there and if it could even work. Well, as you can imagine, the feedback they received was unfortunately the continued release of oil. Yeah, it came down to miswired solenoids and dead batteries, easily detected with the correct control boards and checks. Heck, here at UEI, we have solenoid control boards that read back the open circuit voltage as well as the closed circuit current, making this pretty easy. Think about it. This entire catastrophe, it came down to miswired solenoids and dead batteries, easily detected. So here's some key questions to think about. Has anybody read this report about the root cause, or even heard of the root cause before this presentation? Some of this maybe can apply to your project or your program. How much overlap here is there with your test systems? How many wiring issues do you encounter? Can you diagnose them ahead of time, or do they manifest themselves as a failure? Upon this failure, can you identify the cause? Is it a sensor, a cable, a load, something else? How much solenoid control do you have? How many sensors are you reading? Avionics are you reading and controlling? Speaking of bad cables, here's some stats I found recently. 75% of cables fail and are replaced. 36% of those once a year, 20% of them twice a year. I don't know about you, but every system I have ever seen has cables included. How are you diagnosing these? Or are you just waiting for a failure? So let's build a checklist. We'll review a few methods to sense and diagnose failures with built-in test features, as well as provide you with a checklist to use. This should help make sure issues relevant to your upcoming deployment are addressed. As you know, time and materials add up quickly. Simple things that can be checked and tested can prevent much larger issues later. And as the Deepwater Horizon disaster shows, can bear the worst kind of consequences. So let's start with the basics. Your system should be able to identify shorts and opens. Why shorts? Why opens? Well, remember those cables that shorted everything out? At minimum, you should be able to determine if a cable is connected or if the load is present, or if the batteries are charged and connected correctly. If you have inputs and outputs, have a method to test all of them as you run. It's called built-in test. You may want to consider injecting errors into the tester as well as range testing for the channels. The real question to ask is, can your system pinpoint the failure? And is it real? Is it a sensor, a wire? Is it the hardware? Having a method to verify the complete test setup and connections helps you answer the all-important question, is that failure real? Demand this from your hardware. You should be able to have your hardware designers design it in, but of course, you need to ensure that it's implemented in your software. Here's a pretty relevant example. One simulation company does system-level diagnostics right down to the lights in the cabin inside their simulators. They check everything, and they do some predictive maintenance. The object is to avoid delays in their revenue-generating simulation time. Those simulators are expensive. How do you ensure maximum uptime of your systems? One space launch company does 100% verification of all solenoids as they prepare for launch. Using this data, they can measure solenoid leakage for predictive maintenance. They can also measure the current to determine if a solenoid is stuck open or closed. All of this before launch, and we've certainly some pretty catastrophic launch failures as well. Another good example that's pretty relevant are trouble codes inside of a car. This has been applied to the aerospace industry as well. Cars self-diagnose and present their findings as these trouble codes that I'm sure you've seen. I do wonder if SpaceX has the same trouble codes as Tesla. Anyway, whether it's a tester or control system, if you have the correct feedback, you can also have these trouble codes. There should be built-in test or bit routines for device under test, similar to the reporting of trouble codes on a vehicle, as well as basic range checking for any sensor. Implementing built-in tests for monitoring or controlling systems can eliminate or prevent costly failures. The hardware should be able to check input voltage and current, or even display the internal temperature of the system. Built-in test was originally designed for such in-situ fault finding. However, it is not necessarily accurate. One study describes a typical Airbus A320 that has 2,000 bit events during the day. Of the 17 LRUs replaced, only 2 of those had faults that correlated to a fault in the built-in test log. Built-in tests can certainly be an indicator of issues, but it can also lead to bit exhaustion from false events. Typical bus and automotive applications also have comprehensive bit or built-in tests with trouble codes. Here's another example of bit with trouble codes and an additional external health monitoring system. BAE, working with Alexander Dennis, found they required an external health monitoring system on their line of hybrid buses, the Enviro 200H, 350H, and 400H, even though they use an advanced trouble code system on their buses. In the midst of all this, the UEI system acts as a central nervous system for the BAE system performance and health diagnostics monitoring system. It receives health status and bit information through the CAN and RS-232 buses from various subsystems, such as the energy storage system, the motor, the generator, the power system, the engine, even the doors give us some of these built in test trouble codes. It then relays the information to the fleet health management system for analysis and post processing. This system uploads the data over Wi Fi automatically when it jumps into or when it goes into the bus yard by using advanced analysis software to post process the raw data that is collected live during the bus operation. This system can monitor and highlight trends and outliers and use the data to diagnose potential problems. And as an example, the system was used to properly isolate and diagnose a marginal component, a torn Cobra head boot on the air intake system. The data indicated it needed to be fixed, although there weren't any bit or trouble codes on vehicle diagnostics. And so obviously, the system was not be able to diagnose it on its own. However, looking at the conglomeration of the data, the system could say, hey, I think there's a problem. Isolating and fixing the failing component early on prevented a much bigger problem. Here is the torn intake manifold boot found when it was inspected, based on input from the predictive maintenance system. No trouble code set, yet the system noticed disturbing trends. Predictive maintenance works. Through the selection of data acquisition and simulation boards, you can easily find boards that combine functionality to verify the tester itself. Analog input and output, digital input and output, major avionic protocols, CAN, serial, even customer or GUI inputs and outputs can be checked and rechecked before the test. But what about before deployment? We have been talking about test, built-in test, all for the deployment stage. But what about before deployment? Shouldn't we test the design to ensure everything works as specified? Sounds good to me. And this is what's known as verification and validation, or V&V. So verification and validation are independent procedures that are used together for checking that a product, a service, or a system meets requirements and specifications and that it fulfills its intended purpose. So I copied this from Wikipedia, so it must be correct. Verification is typically testing so that the device or system meets the design specs, while in my mind, validation is more user-oriented, testing that the device or system meets the requirements of the end user's needs. Some of the various methods to verify and validate including HILs or hardware in the loop systems, system integration labs or SILs, and something known as hybrid test benches. So where are you in your development? Hopefully everyone here is familiar with the V development model. Whether you are in software development, hardware development, or the systems, this model is entirely applicable to show how each phase can influence the next, from conceptual models all the way to deployment. Typically, in our world, the closer to the left side of the V is more simulation to prove out concepts, while on the right side is real hardware to be validated against these requirements and models. And of course, I can't forget all of this is moving towards certification at the end. So we can certainly pull out the various simulation and testing needs along the way. Starting with 100% simulation on the left. Typically, the system or unit is simulated using some kind of CAD tool to prove out the concept. As we get into the more detailed design, the more unit testing and component testing is needed. However, some of the supporting signals or systems will still need to be simulated. They may be still under development or just easier to model with a simulation. Many times, this is on a single test bench. Moving back up the right side of the V, after a component is identified as a good candidate, hardware in the loop testing is done for integration testing. More of the other components are real, although some are still simulated. This is done perhaps in a system integration lab or on something called a hybrid test bench. If the candidate passes the verification criteria, sometimes it'll be integrated into a full fidelity simulator so a pilot can, quote, fly it. Better to test it on the ground, that's for sure. Eventually, testing is completed on the vehicle in real world conditions with instrumentation, of course, so we can make sure it's working. There's ample opportunity in this design pattern to reuse models, to reuse the code, and even reuse the hardware. Is this opportunity lost at your company? So let's briefly define some terms. First on the list is a hardware in the loop system. I think we can safely state that embedded systems are best tested with real hardware under real world conditions. However, most times this is very expensive both in time and in cost. So the next best solution is to simulate the hardware with a model and use that to exercise the system, or to test with a mix of real and simulated hardware. This can help with the test coverage since the parameters can be easily changed in a model to a value that should never be seen with real sensors and hardware. Second on the list is our system integration lab, which has all the components in a system to be exercised and tested. Any that are not present can be simulated, as well as most of the signals from the sensors. I've heard the term cockpit on the ground. Many times, this can include an actual fuselage, so a pilot can, again, fly the system while on the ground. And then third is something called a hybrid test bench, and I've seen that term used a lot with our European customers. This is a mix of real and simulated components. Seems to me we should all agree on common terms. So, from my perspective, or the 20,000-foot view, all mean roughly the same thing, or at least they have very similar system characteristics. So what we have here is actually a pretty simple bench or hardware in the loop type system. There we have all the different controllers, the sensors, as well as miles of cable harnesses. So why should we go through this effort? Why cable up all the controllers, the sensors, even the simulated controllers and simulated sensors? Why bother simulating? We should use the real sensor and the real controller. Well, first of all, it saves money. If the controller is not complete, or if it is expensive, why not simulate it? It is also easier to duplicate a simulated sensor or controller than a real one. Maybe only a few are manufactured initially. It also saves time. Many teams can work in parallel. The functionality can be verified before it is actually codified on a board. It also increases accuracy. You can simulate failure modes without the actual failure itself. We can make the flaps fail to work in a sill. However, they 100% need to work in real life. No need to put the sensor in an oven or even a climate chamber. Simulation allows testing outside the normal operating conditions, even contrived or arbitrary ones. Another benefit is the regression test suite. If you have changes, run it against the suite of tests to ensure there are no unintended consequences. Someone once said, trust, but verify. Sure, trust but verify, but don't just verify one point, which actually brings up this next point. So what is the difference between simulation and test? In my mind, it comes down to one word: continuous. Typical test systems test one or more discrete points, while a simulation system or hill or sill, hardware in the loop, system integration labs, they all test a continuous vector type operation. Any signal or system that is simulated must provide the complete range with reasonable fidelity. Are you testing one temperature, or from -20 to 70 C? Every degree between there, or just 3 points? So here's a typical block diagram. The system integration labs, hardware in the loop systems, and hybrid test benches all look pretty similar and very similar to this. We have a controller, or LRU, on the left going through an interconnect panel. This interconnect panel is wired into real or simulated sensors, real or even simulated controllers. Depending on what part of the system you are validating, the sensors could be real or simulated, and the controllers can be real or simulated. Please remember this diagram for later. We're going to see it again. If we look at some of the common signals, there are thermocouples, RTDs, strain gauges, VDTs, even some interesting waveforms, and want to do some Bode plots. And of course, the plain vanilla voltage and current. All these we see inside of many of these hardware test benches and hills and sills. And then we also have many of the communication buses that we were talking about. And then, of course, for the automotive world, they have their own version of CAN and serial and stuff like that. You may need to simulate any of the sensors or controllers on a CAN bus. Here's that diagram again. I promised that we would need it. Everything, regardless of any of those systems, is routed through an interconnect panel. Simulated and real signals, digital buses, even fault signals. So what does yours look like? We've seen quite the contraptions that are prone to errors, as well as a maintenance nightmare. We've seen hardwired, we've seen them connectorized, we've seen people taking all kinds of different cables and routing them by hand. Well, the good news is technology marches on. We all know Moore's Law. We've come a long way from the wire wrap, from the through hole, and even from the chip sockets. All these little ICs are getting smaller and smaller, and they're preserving or even increasing the capability. I don't know about you, but our board sizes are getting smaller. They're using less power, and they're generating a lot less heat. There are now some very small, how about tiny, solid-state relays. They've got specs like 100 milliohm on resistance, switch up to 60 volts on these things, can handle 3 amps, have up to 2.5K isolation, and all on, I don't know, 5/100ths of a square inch, pretty tiny, which is good because now we have a better way to handle these interconnects by using these switches for a computer-controlled 3-to-1 interconnect board. The ability to switch in a real signal, the simulated signal, or even a fault or an open is invaluable for your range checking and your error checking. Or you could switch in multiple different faults, fault high, fault low, fault open. You need to take control of your hardware in the loop, your system integration lab, and your hardware test bench. But what about software? Hardware is great, but it needs software to make it work. There are as many software implementations of these benches and labs as there are benches. How can we abstract out the simulation, the real hardware, and the software so we can focus on verifying and validating your hardware? Well, has anybody heard of VISTUS or ED247? It's a standard defined by EuroCai, the European organization leader in the development of worldwide recognized industry standards for aviation. The standard is also called VISTUS for Virtual Interoperable Simulation for Test of Avionics Systems. Its objective is to define a common standard so that virtual component models can be shared between the different aerospace industry actors during the whole product lifecycle. For example, from full simulation to the hybrid test benches, mixing real and virtual components, to even the simulators delivered after the aircraft to the end user. One of the main aspects addressed by this standard is the virtualization of the analog, discrete, and avionic buses. This virtualization is done by digitizing and multiplexing the information onto Ethernet, which is pretty ubiquitous, ensuring that the timing of the signal is preserved. That last point is the key one. So let's look at a high-level architecture of VISTUS. As you see, everything here is based on the Ethernet bus, with many different components connected to it, from virtual to real to the various tools. So let's see if we can review these a little bit. So we have the real components, real avionics, real sensors, and they need something called a bridge, also called an I/O bridge, or hardware to convert these signals to VISTUS packets, which flow over Ethernet and go to the various other tools. This is where the discrete wiring happens. Virtual components generate the VISTUS packets directly. These are software simulations of any component, and these, of course, can receive VISTUS packets to modify their behaviors. So a real component and a virtual component can interact together on this bus. And then, of course, up top, we have all the tools. They include recorders, playback devices, display tools, air injection tools. Any one of these either consumes or generates these VISTUS packets. So a message or a signal can either be generated virtually or from a real component, put on the Ethernet bus, and then consumed by something else who needs it. The receiver does not know if this was generated by a real device or the simulated one. It's just a UDP packet. So why does this work and why does this help? Since there are no wires, the behavior or system can be virtualized. Once a model is defined at the component phase or the conceptual phase, it can be reused all the way to the training simulator at the end and anywhere in between. It works for local testing of a component. It works for system testing of the larger systems. The components can be added as they're available and virtualized when they're not. Models are being reused for validation and testing, and even for the flying trainers on the fully vetted and deployed products. How can this help your design process get off the ground and flying? Well, as we see, every step in the process must have a laser eye on mission critical aspects in the design, verification, and deployment. Design it correctly, verify that it works, and ensure you have built-in tests for your deployed systems. Now, I think it's time to turn over to you for any questions. Well, we've got a couple here, one of whom says, is testing possible for time-triggered systems?
Yeah.
Let's see. So time-triggered systems, if it's TSN-based or time-sensitive networking with an embedded event-triggered system. So in my mind, it means that you are controlling the triggers. So yes, of course, many of our systems that we've done have a master oscillator that is in total control of software, which means yes, you can control any different kind of rate, any different kind of dwell time, any of that. And again, part of it is having your hardware set up correctly in the beginning.
Balaji has put some follow up questions in there. I'll just publish them as they're coming in. Okay. Time with embedded event triggered systems with different rates. Ethernet versus TSN.
Yeah, time triggered Ethernet versus TSN. Those are two similar but different protocols over Ethernet. And yeah, we have the ability to test TSN and to mess with some of the scheduling in TSN. We don't have that for time-triggered Ethernet. I think you would have to speak with the owners of that IP to do that kind of stuff. But yes, to your point, testing a TSN system is becoming much more complex, and you need to have the hardware and the IP ready to do that. Absolutely.
Okay. All right. Thanks, Eric. This one from Gary Stevens, it doesn't make an awful lot of sense, but I think he's got some acronyms going on here. As a manufacturer of high-end aerospace systems, what is most needed? It's quite a general question, I guess.
Well, for my statement, what's most needed is in the verification and validation phase, or the V&V phase, making sure that you are handling all the edge cases, all the end cases, and ensure you can make, quote, your failure modes and make sure your system handles those failure modes in a manner that it's supposed to.
And here's one from Vinod Kumar, who is asking how to overcome timing related issues when similar systems are replaced with a new one.
How to overcome them. I think one of the things that we're talking about is testing for those and ensure that everything is testing to ensure you don't have these timing related issues. So trying to get the characteristics of the old system versus the new system, and then testing to ensure that they're all within the same envelope. Definitely.
So we've got a couple more questions. This one again from Balaji MK. He would like to ask if UEI switch hardware using TSN can use fiber optic testing. Is the testing hardware available or possible?
Let's see. So there's a couple questions in there. These questions keep moving around. There we go.
There we go. Sorry. Just if you stick in the published column, I'll read them out and then publish them. Sorry, Eric.
Sounds perfect. Let's see. So we can certainly test the TSN piece. We would need a fiber to copper converter. So yes, there certainly is hardware available to do some of this. UEI does not have switches. So you would need to procure your own TSN switch, but we certainly have hardware as an end device to test anything on a TSN network.
Okay, thank you. And this one from Heidi, Heidi Ozard. She would like to know, is there a time relationship between the concept of operation and the V&V period?
Is there a time relationship between the concept of operations and the V&V period? So I would say you would really want to test as soon and as often as you can. So even at the conceptual phase, if you've got models, that's really what you're doing, is testing your models or your simulations to ensure you're going to get your control loops running correctly, getting the right type of control. As you codify some of it into hardware and software that's going to be deployed, you would continue your testing to ensure that, yes, you have fulfilled what was in your concept on your actual hardware and software. So as soon as possible, you should be doing this testing. You want to catch them early and not later, that's for sure.
Bob has got one. Okay. Bob would like to ask, how can an engineer learn more about UEI's testing and control options? It sounds
That's
like
a great question, Bob. Let's see. So you can certainly come to our website at www.ueidaq.com. We've got lots of material there, a lot of tutorials, lots of videos, lots of information. And please feel free to reach out to me.
Okay,
and I
great.
believe the last slide has my information. Am I showing that?
Yeah,
last
I'm
slide?
not sure what's happened to the last slide.
Where is that last slide? I don't know.
There you go.
There we go. Thank you so much.
Well, that looks about it. I mean, that's that. I'd like to thank the audience for their attention and the questions at the end there. There's some great questions, and thanks for that, everyone that's registered and turned up. Eric, do you want to finish up? Have you got any final thoughts? Or
I just want to thank everybody's time today, and I hope certainly you have a good Friday tomorrow.